What if the exact thing you thought was making your AI agent smarter is literally the reason it keeps failing? Welcome to the hidden layer, Decoding Artificial Intelligence. Today we're decoding a breakthrough in agentic memory that's going to fundamentally change how you, as an applied engineer, build verifiable AI.
Because here's the massive paradox we are tackling today. Giving your AI agent perfect, exact, step-by-step memory from its past tasks, it actually causes it to crash on new ones. I know, it sounds crazy, right? But flawless recall is a trap, and we're going to show you exactly why.
So, in this explainer, we're diving deep into mastering memory transfer learning, or MTL for real-world engineering. I'm going to show you exactly how to apply this to build self-evolving agents. And stick around, because a bit later, I'm opening up a loop on a really counterintuitive secret about memory abstraction that guarantees your AI won't accidentally sabotage itself. Let's get into it.
Section 1. The AI memory problem. Right now, there is a huge gap between how we build memory and how we actually should be building it. Think about it. Most self-evolving coding agents work in total silos. If your agent solves an SWE bench task, it only remembers SWE bench data. It completely ignores the reality that completely different coding tasks, like, say, competitive programming or machine learning research, they all share the exact same underlying infrastructure. I mean, they're all using Linux shells, they're all writing Python, they all have cross-file dependencies. By keeping memory locked up in these single-domain silos, we are literally starving our agents of a massive pool of shared foundational knowledge.
Section 2. Memory transfer learning. So the fix for this silo effect? Memory transfer learning, or MTL, which involves transferring memory across completely different coding tasks. And guys, the numbers here are wild. By pooling memory across heterogeneous domains, researchers hit a massive peak performance jump of up to 8.3% on benchmarks like MLGym Bench. Just to give you an idea, the baseline zero-shot agents were scoring around 66%, but when you plug in MTL, boom, they shot up to 75%. Across 6 different coding benchmarks, average performance bumped up by 3.7%. So the big takeaway here? Cross-domain knowledge isn't just some nice theory. It translates to immediate, real-world gains. And the empirical data backs this up perfectly. MTL consistently beats out standard self-evolving methods by up to 2.9%. But here is the crazy part. It does this while using just a tiny fraction of the memory pool. Some of the older methods out there tried stuffing in almost 6,000 memories, and they still couldn't keep up. The MTL approach got superior results using only 431 highly curated memories. That's massive efficiency and effectiveness, all rolled into one.
Section 3. The meta-knowledge secret.
Okay, remember that secret technique I promised you earlier? Here's the catch. Transferring the wrong type of memory will actively sabotage your AI. When researchers looked at 4 distinct memory types, trajectory, workflow, summary, and insight, they noticed a huge divide. If you transfer raw code traces, which are called trajectories, it literally causes distraction. It causes what researchers call negative transfer. Basically, if you hand an agent the exact step-by-step terminal commands from a totally unrelated past task, it just tries to blindly copy-paste them. It gets super bogged down in the weeds of task-specific details that have absolutely nothing to do with the new problem. So, if raw code is out, what do we actually want? Well, the real magic is in extracting meta-knowledge. Meta-knowledge is generalized operational know-how, it's procedural guidance instead of raw domain-specific execution logs. It's not telling the AI what code to write, it's teaching it how to approach the act of coding itself. Think of it like putting up behavioral guardrails.
Let's break down exactly what this meta-knowledge actually does for you. This transferred memory basically teaches the agent how to act like a pro. It makes sure the agent sticks to strict verification procedures, like, writing a test before submitting a fix. It enforces API compliance and interaction protocols. It also teaches the agent anti-pattern avoidance, so no more massive, brittle, one-shot refactors or hard-coded fixes. Instead, your agent learns environmental adaptation, meaning it makes safe, step-by-step modifications. It's essentially learning the discipline of a senior developer rather than just blindly copying a junior dev's messy code snippets.
Section 4. Abstraction dictates transferability. This leads us right into an absolutely crucial architectural rule for your tech stack. Abstraction dictates transferability. Highly abstract insights become task agnostic, and they generalize beautifully across different domains.
In the original research, when they actually mapped these memory formats onto a visualization graph, the highly abstract insight embeddings just seamlessly blended together across different benchmarks. On the flip side, the low abstraction trajectories, those raw execution logs we talked about, they clumped into rigid, isolated clusters. They hold on to way too much specific detail and just end up confusing the agent. So by explicitly prompting your memory generator to strip out specific file names and focus purely on the big picture lessons, you finally unlock real cross-domain transfer.
Section 5. Building verifiable AI agents.
All right, so how do you, as an applied engineer, actually use all this to build robust, verifiable agents right now? This is exactly where the AI Genie framework comes in to structure your implementation. You're going to want to build a 3-step offline to online pipeline. First, during your offline generation phase, use the AI Genie framework to have an LLM extract high-level task-agnostic insights from your past trajectories, both the wins and the fails. Second, take those insights and store them in a unified cross-domain memory pool. Seriously, tear down the walls between your different coding tasks. And third, during active inference, retrieve these insights for procedural guidance. You don't feed them into the system prompt as code templates. You feed them in as strategic rules of engagement for the agent to follow.
And I have to show you this incredible real-world example straight from the study. This is a SWE-bench Django case study. The baseline agent completely tanked the task because it blindly submitted a fix that broke the whole system. But when they turned on MTL, an insight transferred over from a totally different domain, live code bench, and taught the AI a brand new behavior. The agent retrieved a memory saying, "Create quick self-contained tests using an inline Python here doc." The agent literally followed this advice, wrote its own inline test to verify its fix before hitting submit, and turned a complete zero-shot failure into a verified success. I mean, that is the literal power of cross-domain procedural transfer in action.
This completely flips everything we thought we knew about AI memory design right on its head. We really have to stop treating agent memory like a dumb hard drive full of raw execution logs, and start treating it like a refined playbook of engineering wisdom. Which leaves us with one vital question to wrap up on. How will you restructure your agent's memory pool to evolve from simple, brittle recall to true cross-domain wisdom? Take a look at your current pipelines and start abstracting today. Thanks for hanging out with me on this explainer, and keep building.